The compressibility factor is a factor used to measure how much the properties of a real gas deviate from the expected properties of an ideal gas. It is represented by Z and is a dimensionless ratio. The equation for Z is as follows.
Before looking at calculations of how to find Z, it is important to understand what Z shows. If Z is equal to 1, then it is an ideal gas. Based on this, we use our Z value to see how other gases deviate. The closer it is to 1, the closer it is to behaving in an ideal manner. In order to find the value of Z, we read it off from the generalized compressibility chart for various gases. But in order to examine this graph, we first need to look at what TR and PR. Reduced temperature is denoted as TR and can be calculated using the equation on the screen. Reduced pressure is denoted as PR and can be calculated using the equation on the screen.
Let's look at an example where we have to determine the value for Z using our compressibility chart. We are given ethylene, its temperature, and its pressure. We know that in order to read the compressibility chart, we need a value for TR and PR. We can easily find these using this equation and this equation. We are given our T value, we're also given our P value. We can find our TC value and our PC value using table A1 of the thermodynamics tables. We then substitute our values into our equations. Note that for temperature, we have to use Kelvin. That's why we add 273.15. And for pressure, we converted kPa to bar because PC was given in bar and we have to stay consistent with our units. Now that we have our values for TR and PR, we can look at the compressibility chart. Firstly, we have to see what shape represents ethylene. And we can see that it is a circle. And now we can look and see TR is equal to 1.1 on this line and PR is equal to 2.0 on this line. And here we have a circle that represents ethylene, and we can see that ethylene has Z equal to approximately 0.4.
Observations from the graph. Now that we understand how the chart works, we can make the following assumptions. As TR increases in value, Z tends to 1. We see that TR ends at 2 and the line tends to Z equals to 1. Thus, we can assume that when TR is greater than 2, the gas behaves like an ideal gas. Through analysis of the equation of reduced pressure, we can conclude that there is an inverse relationship between PR and PC.
Let's look at this example where we have to use our equation for Z in order to calculate. So we are given 3.5 kgs of propane. We are given its pressure as well as its initial temperature and final temperature. We are asked to find the initial volume. We have to use our equation because our equation incorporates V, which is what we are looking for. Before we begin, it is important to note that firstly, they asked us for initial volume, hence we have to use initial values when we substitute in for our variables. Secondly, they ask us to calculate volume in meters cubed, so we have to use values that accommodate this and units that accommodate this. Lastly, we can manipulate our equation to make V the subject of the formula. This makes it easier. When we do this, we get this equation. Now we can see that we need a value for Z in order to solve this. We can easily find our values for TR and PR using these equations, and thereafter we can read Z off of our compressibility chart. We can see that Z will be equal to 0.54 approximately. Once we have this, we can substitute into our equation. Note that M represents molar mass and it can be found on table A1 of our thermodynamic tables. We then substitute into our equation. And please note that we use our R value as 8314 because these units better align for us to find our answer in meters cubed than when we use 8.314. Once we find our Z value, we can see that the units are meters cubed per kg, but we want our answers in meters cubed. So we have to multiply by the mass in kgs, and then we will get our V alone as this value.
An alternative method using the thermodynamics tables. We can calculate V using the thermodynamics tables. We have to find the saturation temperature of propane at 40 bar and compare it with the initial temperature to see what phase our propane is in. We see that T is greater than T saturation, therefore it is in the superheated phase. We now use table A18 for superheated propane and find V at 40 bar and 110 degrees Celsius. We see that the V values are similar, hence either method can be used.